universe is, how amazing the night sky, a number of events during the year, starry nights where we also do telescope making here. So we've got many activities that we do here. It really is a great place, and you're very friendly country people studying within Australia itself, the solar system, or the stars, or
Welcome, visitors, to our VASTROC 2021. It's with great delight that I welcome you on the Wadawurrung country and all the broader countries across Victoria, and with respect to the past, present and future peoples that we all now share the night sky with. Firstly, I'd like to thank the ASV's President, Dr. Chris Fluke, for allowing the ASV to co-host this precedent VASTROC, the 18th VASTROC in 2021. We are streaming live now across several societies, including the Astronomical Society of South Australia. And it's very exciting that we can still continue to have VASTROC despite I am now in lockdown and several members are in lockdown, so we have to cancel the on-site activities at the observatory today. I'd like to welcome our speaker, Professor Chris Fluke, Swinburne University of Technology SmartSat Professional Chair and Space System Real-Time Data Fusion and Integration and Cognition work. Thanks very much, Chris.
Great. Well, thank you so much, Judith, for the invitation to speak today. It's great that so many people are still able to join online, although I'm sure we would all much rather be sharing stories and ideas and all the exciting things you've been doing in person. And I hope that you can return to those sorts of in-person activities very soon. So this morning, I'm going to talk a little bit about some of the research work I've been undertaking over the last few years and give you a vision perhaps of what the future of professional astronomy might look like. And I'm going to pose a question for you. What is the point of humans? With a very important caveat there when we're talking about data-intensive visual discovery. I'd like to do my own acknowledgement of country. I acknowledge the Wurundjeri people of the Kulin Nation, who are the traditional owners of the lands on which I live and work in Melbourne. I pay my respects to their elders past, present and emerging. And particularly of relevance for what I'm going to be talking about today is acknowledging the important role that the traditional owners of lands all across Australia have played as amongst the first scientists in the world and also the first creators of tools and technology. Because I'm particularly interested in the tools of astronomy and how they're changing over time and what they might look like into the future. So as a bit of additional motivation, a quote here from Freeman Dyson, who said that the progress of science requires both new concepts and new tools. And so a great deal of modern astronomy is about understanding new concepts, thinking about new types of objects, continually refining our understanding of things that we thought we knew all about. But in order to continue to make new discoveries, we also need new ways of making those discoveries, new types of tools, new types of technology. So in preparing for today, I was thinking back on some of the very first talks that I gave about astronomy early in my career, and using two pieces of technology that I'm sure a number of you are very familiar with. But when I talk to younger audiences, they have never seen either of these things. We've got a set of slides and an overhead projector. And certainly my earliest presentations of research results were handwritten on acetate slides and placed on the overhead projector, hopefully the right way round so that the audience knew what I was talking about. But I think it's extraordinary that within a period of only about 25 years, we've gone from those technologies that were all that we had as a way of communicating about astronomy to diverse audiences to today. I'm sitting in my home, you're sitting in your homes, we're streaming live, we have all of this digital data, all of these new technologies and new ideas and new methods, and an optimism that there'll be lots of new interesting technologies still to come and new discoveries to be made about the universe. So we are in what we consider to be an era of data-intensive astronomy. And I'll use that phrase in a couple of different ways this morning. But really, it's about saying that we have an enormous quantity and quality of data. And the reason we have so much data available to us is in part due to the improvement in the technologies that we have available. So if we have a quick look at a kind of a timeline of some of the important astronomy technology, the Astrolabe here, I guess the iPad or the iPhone of the time 1,000 years ago, any self-respecting astronomer would have their Astrolabe on hand, ready to observe the locations of some key stars, turn it around and do some calculations using the information engraved on the back. Then in the 17th century, we had the commencement of the telescopic era, the change from simply recording positions of astronomical objects, noting whether there were new phenomena occurring or not, occasionally having something exciting like a comet appear, to being able to explore and study astronomical objects in more detail. The discovery of moons around Jupiter, rings around Saturn, craters on the moon, all of these things that were previously beyond the reach of astronomers. Once you start to build telescopes, then you want to start building larger and larger telescopes. And of course, a telescope that's very important to many of you, I'm sure, who are listening in this morning, is our own great Melbourne Telescope. And the ability to see further, to see fainter, and to see more of the sky, depending on how you configured that telescope. But telescopes on the ground have limitations. We have an atmosphere that distorts our view, and so we can collect better and clearer data by putting telescopes into space. And not only can we do that, but we also start to explore a multi-wavelength universe as we add in radio telescopes, UV, infrared, microwave, X-ray, gamma ray telescopes, and so forth. So in each case, we've introduced a new technology, we've been able to look at the universe in a different way, and we've vastly increased both the quantity and quality of data that we're able to collect. But there's something else that happens when you introduce a new technology. You actually change the way that astronomers work. So now I want to look at the development of the astronomer over time. And I'm going to start with the telescopic era and what we might call the artistic astronomer. So you would look through your telescope, as you all would do, and I'm sure there are quite a few artistic astronomers in the community here today. And the ability to actually record detail that you could share and discuss with other astronomers was in part dependent on your skill at capturing accurately what it was that you were seeing. I would say from a personal perspective, I would be a terrible artistic astronomer. So I'm glad that that's not a technology that I'm dependent on. We then move on to the photographic age, and now you can go from a more subjective view with artistic astronomy, where it's based on your individual artistic skill, to one where now you have a much more objective representation. Although the camera can lie, we have a much greater chance that we are recording accurately what we're seeing, and also recording things that we can't see with our own eyes, because photographic plates, even the very early versions of those, were more sensitive than the human eye. They can record photons over a longer period and therefore see fainter and fainter detail. But you can then move from a photographic version of your data to a digital version of your data. And the CCD, again, revolutionized the role of astronomy, but also, again, changed the way that astronomers were working. In the photographic age, I would need to have these very large plates, or I would need to print them out in some fashion. If I wanted to share them with colleagues, you know, do I send an original plate? Do I send some kind of a photograph of that? Versus a digital way of collecting data, I can now transfer that in a much more easier fashion. And I have some other advantages as well that come with a variety of ways of improving my digital recording of data. And that actually led on to what we can think of as the Virtual Observatory Era. So digital recording, the CCD was developed in sort of the 1960s and 1970s, eventually, you know, completely replaced the prior photographic age, in the same way that the photographic age essentially completely replaced the artistic age. The Virtual Observatory was a concept that said, well, you know, astronomers don't actually need to go to telescopes anymore. We can just automate the process or have a small number of astronomers do the observation for us. And actually the way that we are supposed to do astronomy is to put all of the data into archives, and you would do all of your discovery work that way. Well, it didn't quite work out the way that it was imagined. It was a very complex and challenging approach to software. It was a challenging approach to how we worked, but it has certainly brought us into an era where astronomers share their data with others. They make it available. They certainly use archives. They certainly are preserving more and more data. They're recognizing the legacy value, not only of data that was recorded in the past, but also the value that the data recording now will have into the future. And so we are still probably in this virtual observatory era, but it has a different feeling to it. But it is certainly true that astronomers are no longer going to observatories as often as they did. That a lot of the work, particularly with some of these very large radio telescopes like the Australian Square Kilometre Array Pathfinder, the Meerkat instrument in South Africa, most of the time you are using those by accessing data out of an archive that has been recorded. Today, I'm going to speculate a little bit about what might be coming next. What might the next version of the astronomer be? So coming back to our data-intensive problem then for a moment, that the volume and velocity of modern data is posing many challenges for how we undertake traditional visualization-based knowledge discovery. There's a lot of words in there that I need to define for you. Volume is simply about the quantity of data that's available to us. Velocity is how quickly that data is appearing, or how quickly we need to process it or analyze it for it to have value. If we can collect this data, but we can't process or use it, then what was the point in collecting it? Traditional is really about saying, well, what have people been doing most recently? So traditions obviously change over time. And so tradition at the moment for most astronomers is doing processing either on your desktop computer, using a fairly conventional 2D monitor. Perhaps you're using a remote supercomputer or some other device as well. But this other part, visualization-based knowledge discoveries, where a lot of my own research focuses on, when we look at images, when we look at representations of data, how do we make discoveries? How do we gain insight? How do we get new understanding? So this is, I guess, the challenge that we're now facing with some of the new observatories and telescopes and facilities coming online, that the vast majority of data that will now be collected in astronomy will never actually be looked at by a human. Compare that to what was going on in the end of the 19th century. We have this amazing team of women here, the Harvard computers. In the scene here, you can see third from the left is Henrietta Leavitt, who made the discovery of the Cepheid period luminosity law that was absolutely essential for our understanding of the distance scale. In the foreground, we have Annie Jump Cannon, who made many contributions to the understanding of spectral classification of stars, and other great astronomers in there as well. Wilhelmina Fleming is standing in the background. So in the 1890s, they made discoveries by looking at every single photographic plate that had been recorded from the Harvard College Observatory. Today, we're talking about data sets collected from radio telescopes like ASCAP, like the Future Square Kilometre Array, where maybe less than 1% of data will ever be looked at by a human. So if we're not going to look at it by a human, who is going to look at it? Well, here's two more terms that are becoming increasingly familiar to astronomers: artificial intelligence and machine learning. AI is all about computers performing tasks that would normally require some kind of human intelligence. And we're surrounded by AI today. It recommends what TV shows we should be watching, a whole host of different activities that go on where we're being, decision making is being performed for us rather than a human performing those tasks. Machine learning and AI and machine learning are often sort of very closely mashed together, but they are slightly separate concepts. Machine learning is all about automated processes that usually learn by example, or they make discoveries themselves within data. It's computer programs that are doing machine learning, and as opposed to normal programming where you are writing an algorithm to solve a specific problem, machine learning is often, we don't have any idea what it is that we're trying to learn, and the computer learns itself in order to help us to classify, predict, discover, or even generate new data. So these are what I'm going to sort of call collectively automated methods. So if you have more data than you can possibly look at, then the expectation is that our automated approaches are going to play an ever increasing role. And I like to present this as a sort of a continuum or a spectrum, where on one side we have visual cognition. A human looks at absolutely everything. And that's the situation we had with our Harvard computer. On the right-hand side, we have our entirely automated part of the spectrum, where all of the work is done by AI or machine learning, and a human never looks at anything. Well, as an astronomer, I'm a little bit sort of, disappointed if that's the way the future is entirely going. I want to still do something. I still want to look at things. I still want to have opportunities to make discoveries. I don't want the computers to have all the fun, because they probably don't even realize that they're having any fun. But even if we think that automated approaches are going to play a very large role, there is still an important role for humans at all stages of data collection, whether that's planning an experiment, doing the actual collection, quality control, have the images been collected correctly, analyzing the results that come back, and then publishing and presenting those results to a variety of different audiences. So we have two challenges that I'm going to touch on as quickly as possible this morning. How do we support visualization beyond the traditional desktop? And can we actually improve the way that humans work with machines? So to do that, I want to tell you a tale of two, what we're calling tiled display systems that you can see here. We have at the top the Cave 2 that was operating at Monash University from about 2013 until 2020, and the Swinburne Discovery Wall at the bottom part of the screen there. And so my first introduction to this facility, the Cave 2, came about 10 years ago, trying to understand with a colleague, David Barnes, and another colleague of his, Govinda Powdell, a medical imaging issue, which I won't go into today, but it was all about finding evidence of Huntington's disease, which is a neurodegenerative disease. And the problem that they were having was having to look at data from one patient at a time, which was proving to be a very inefficient way of looking for common features between multiple people. The Cave 2 itself as a facility was 80 stereoscopic screens arranged in this sort of circular shape cylinder. It's about 6 or 7 meters across, so quite a large space to be working within. And the way that we were trying to use that was saying, well, we have 80 screens up there. We could look at 80 different examples of data at one time in order to drastically impact the speed at which researchers were able to make discoveries by seeing all of the data there in front of them and being able to move pieces of information around, try and look for common patterns as well. And that's also something that we increasingly need to do in astronomy. And this is some work now done by former PhD student from Swinburne, Danny Vole, standing again in the cave too, but now looking at data that's been collected from various radio telescopes. So each of the cubes there is containing data about one galaxy. It's showing the distribution of neutral hydrogen, very important as part of the understanding of the life cycle of galaxies. Neutral hydrogen is only visible with a radio telescope. And we can also get information about how that hydrogen gas is moving around. So it's quite a complex three-dimensional structure. So this was some software that Danny created that would allow us to do these sort of very large collaborative, what we're calling visual analytics tasks, being able to see lots of data, manipulate it, find patterns, find interesting things in that data. So we were then looking at putting together our own version of that facility at Swinburne, the Discovery Wall, with about 100 megapixels. So you can go and build one of these yourself if you would like. All you need is a very large number of 4K monitors, a number of high-end graphics cards, and as many PCs as you can get your hands on to run this facility. But again, now we're looking at some of this data from measurements of the hydrogen gas in galaxies. And so we're able to look at multiple galaxies at the same time. And as an example of a quality control process, you might note that one of those cubes had quite a lot of purple signal in it, which is suggesting that a little bit more work was required in order to clean up that data ready to be processed. So we have a challenge when we're creating very large non-traditional facilities. This is really now taking the astronomer away from their desktop and presenting their data in a very different way in the hope that they can now make a discovery that would be very hard to make on a simple desktop display. But just because you build these things, will anyone, our humans, our astronomers, the people that we want to use them, will they come along and actually take advantage of them or not? So the way you find out is you have to experiment on humans, which is a great deal of fun as an astronomer. It's not something that many astronomers, I think, have got to do over the years, but it's something that's a piece of my own approach to research, is to bring in astronomers to show us how they work, to understand and work with them, how we can improve the way that they're working. So this was some experimental work that was done with Bernard Mead, who was my PhD student at the time. And we were performing a visual search task. Now, there's quite a lot going on in this image, so I'll try and walk you through the different parts of it. So on the left-hand side, we have our standard desktop display, which is actually showing the same image as the entire tiled display wall. So we have, in this case, 24. These were standard monitors, 24 of those monitors altogether. So instantly you can see that on the standard display on the left, the image is very small. You're going to have to zoom, you're going to have to pan, whereas for the tiled display wall, you can stand right up, you can walk around, you can have multiple people there. And then we would show our participants an object and ask them to find it on one or other of the displays. And we recorded how well people did. We looked at how fast they could do it, how many types of objects they could do. We provided some calibration tasks where they had to find words rather than looking at astronomical images. We even performed some sort of Where's Wally style experiments, but unfortunately the copyright owners of Where's Wally wouldn't allow us to ever use any of the pictures anywhere to show you what happened. What was interesting to us when we compared performance on these two different displays and different ways of making discoveries and finding objects is that there wasn't a great deal of difference. The performance on the tile display wall was better than a standard desktop display, but not very much better. And that might be because of the short term on which we were doing the experiment, that people were unfamiliar with the technology, or actually there might not be that big a difference when it comes down to it. But what we did see a difference in was the attitude of our astronomers, and in this case we had a large number of non-astronomers as well, the attitude towards whether one or other of the displays was easier to use. So for our standard desktop display, most people thought that it was not easy to use for the task, but the tile display wall was easy to use. Was it a suitable display? Well, the standard desktop display was not considered to be a suitable display for looking at and discovering small features within very large images, but the tile display was found to be suitable. So this is actually quite interesting, that if you're asking an astronomer to perform a task over and over, but you're giving them a display that is not easy to use and not terribly suitable, then what impact are you having on their ability to work as effectively as they could? Are we actually limiting the ability of astronomers to make discoveries, to find connections, simply by restricting them to a standard display which is not fit for purpose? To then find another application where the tile display wall was actually a suitable display to use, because we were seeing lots of people writing about tile display walls are fantastic for astronomy, but we had no evidence that anyone had actually used them for anything beyond displaying images to the public. So this takes me on to our final case study for this morning, a project called Deeper, Wider, Faster. And I've added the extra word cyber there in order to explain my own contribution to this project. So there's some interesting similarities here between our Harvard computers from the 1890s, and on the right, the Deeper, Wider, Faster team in action in our control room. First of all is the team-based approach. It's not one person sitting in an office on their own doing a task. It's a large number of people in there together. And also we have people doing slightly different things. Now, I can't tell you whether the Harvard Computers image is really a demonstration of how they were working, or if that was more of a staged photographic opportunity. But certainly on the right, this is the team at work. We have lots of different types of displays there, people on their laptops, people looking at our tile display wall. At the back of the room, you can see a video conferencing connecting astronomers at Swinburne University to astronomers who were located in Hawaii, in Japan, all sorts of different locations. So an international team working together. And this is what to make some discoveries related to a class of objects called fast radio bursts. And you may hopefully be familiar with these objects now. They've been part of the astronomy literature for well over a decade. I will call them FRBs, just to be quick. So what they are, as the name suggests, they are very short-lived or fast objects. They are a signal that exists for perhaps less than 5 or so milliseconds. There are some that are repeating, and I won't try and explain the origins of those. They were not at all expected when they were first discovered. They are found at the moment using radio telescopes, and so the Parkes Observatory, the Molonglo Observatory, are two of the key facilities internationally, and also ASCAP, key facilities for finding these new fast radio bursts. On the left-hand side, the data that I'm showing there is one of the original discovery images. We have an x-axis showing time and a y-axis showing the frequency of observation. And the characteristic signal for a fast radio burst is this sweep in time as the frequency is decreasing. what's actually happening is a signal is propagating through the universe. It encounters clouds of electrons, and those electrons delay parts of the signal depending on the frequency. So the high frequency arrives first, and then a very short period of time later, the lower frequencies arrive. This data example here was recorded in 2001 from, I believe it was at the Parkes Observatory, but it wasn't actually analysed until 6 years later. It took a long time until the computational power was available to perform the analysis that led to the discovery, and people weren't expecting to see these things, so it was a serendipitous discovery. But we now know of, I'm going to say dozens and dozens of these objects. We believe that they are occurring at a very high rate every day. They're a significant driver of new research, new techniques, and new understanding of the complex environments around stars, likely to be due to catastrophic events of stars colliding, exploding, falling to black holes, all of those types of phenomena. So the Deeper, Wider, Faster project was hoping to find the optical counterparts of these fast radio bursts. And this was the vision of Jeff Cookie, an associate professor at Swinburne University, and then significant contributions from his PhD student, Igor Andrioni, who then went on to a postdoc at Caltech, and Tyler Pritchard, who was a postdoc at Swinburne, who I believe now is at New York University. That's Jeff on the right and Igor on the left, and in the middle is submitted her PhD in the last few weeks, working with Jeff on the analysis of some of the Deeper, Wider, Faster data. So what they hope to do is that a fast radio burst would occur, that a radio telescope would identify it in close to real time, and then by having a very large number of telescopes all looking at the same location on the sky, they would be ready to catch the optical afterglow. Now, this is a very tricky thing to do. There's a great deal of luck that goes into this. You only have very short periods of time in which you're running your observing program, and although they've not been able to find an FRB counterpart, they have detected and discovered a very large number of short-lived transients and done some incredible work. But also one of the amazing things that Jeff and his team have been able to do is coordinate literally dozens of telescopes, professional grade, all over the world, satellites, all working together in a way that's never happened before throughout astronomy. So that's just an extraordinary achievement. The flow of data, one of the primary telescopes is this instrument called DECAM in the Cerro Tololo Observatory in Chile, and it is recording this. You can see the number on there. Essentially the equivalent of a 4K telescope, 4K television, 59 times every 20 seconds. So it's an incredibly large detector with 59 individual CCDs, each of them with a 4K resolution. So there's this enormous quantity of data that then they need to perform what's called a subtraction or difference imaging, where they compare the current image with a previous image. They then look for anything that's changed in brightness, and then they have a machine learning tool, which was built by Igor, that finds what they think are interesting objects to look at. And this is now really coming back to now, what is the point of our humans? So one of the ways that machine learning works is you give it examples to learn from. But we have, in many cases, when we're discovering something new, a no template problem. We have no idea what it is that we're looking for. So we don't know how to automate that process. It could be that we're trying to find the origin of fast radio bursts. We could be looking at interesting new ultra-fast transients, kilonovae, which is a different type of supernovae, but we have no idea what the specific feature is going to look like. So we absolutely need humans involved in this process, because they make clear decisions on what's interesting for us to follow up on. So that really now is the way that I like to look at this team here, a collaborative environment of people making decisions in real time, but also recognizing that the people in this room have different skills. And at different stages of their work, they need different types of support to do their very best. So that leads me now, and I'll perhaps in the interest of time, I'll move through this as quickly as I can. This is the software that is partly used to help them with their decision making. And I've highlighted there all the different places in this room where this perceived decision making platform exists. And this is work done by my PhD student, Sarah Hegarty. The astronomers are presented with relevant information that allows them to make a decision. And this is presented to them in a fairly simple web interface. And because it's in a web interface, we're able to track what they're doing. So while some of these actual observing campaigns for deeper, wider, faster were running, Sarah and I were recording information with the consent of the astronomers about what they were doing. Because ultimately, we wanted to understand, how do they make decisions? What information on here allows them to say that this is an asteroid, or this is a variable star, or this might be the most interesting object that we've ever seen? So they're presented with data, and they're presented with a set of decisions that they can make. And we've been analysing and thinking about their decision-making workflows and decision-making performance. So we break people down into either novices, they're new to the task, or they're experts. They've had some additional training. They understand what it is that they're trying to do. And we look at their workflows. And we're still trying to understand exactly what all of this means. We have user interactions where the mouse was moved on the web page, and you can see that different users move their mouse around and do all sorts of things. We have decision-making workflows from the first time they see an object until they make a final decision on what it is. And our novices tend to make lots of different types of decisions. But our experts, although we can't exactly explain what they're doing different, the difference is that experts have more ideas straight away about what it is that they're looking at. And so they barely move the mouse around, and they almost instantly say that everything is not interesting. So we're trying to now understand, as a next stage, how do we use this information? Can we actually automate our assessment of skill? Can we think about the workload of astronomers? Deeper, Wider, Faster is showing us a little bit about what the future of astronomy is going to be like. When new instruments like the Square Kilometre Array come on, and we're collecting petabytes of data every day, exabytes of data every year, automated systems sending out millions and millions of candidates for people to look at and try and work out what they are. How do we begin to think about supporting them? So I think, in my view, the next version of the astronomer is actually the cyberhuman astronomer. It's not replacing the astronomer entirely by artificial intelligence, but it's about helping astronomers to work more tightly with our machines, work smarter, be supported when they need to, be trained when they need to, and perhaps that might be what Deeper, Wider, Faster is starting to show us the next generation of astronomers will look like. So I'd like to finish off by saying that it's all about finding balance to create better humans and better astronomers. There is this spectrum between looking at everything and letting the computer do everything. But what if we could find a perfect point between those for every individual and for the team and for the particular discoveries that we were trying to make in order to get the very best outcome? And rather than just creating artificial intelligence to do the hard work for us, what if we could also design artificial intelligence that learned about the way that we work and support us to do our very best work? And that's not contained to astronomy. So to finish up, the volume and velocity of modern data sets is posing challenges for traditional approaches for visualization-based knowledge discovery, which we can actually address by using non-traditional displays, new use of computing, taking advantage of artificial intelligence and machine learning at the right times to get a better outcome. And there is an important point to having humans. First of all, humans continue to ask very interesting and important questions. And ultimately, that's what science is all about. It's not just stamp collecting. It's not just classifying. It's about understanding what it is that we're seeing, generating new theories and new knowledge, and going out and thinking about what else could be out there. Our automated systems can tell us what we find, but they can't tell us why they find it or why it's important. Personally, humans are great for experimenting on, and I'm very grateful to the humans who have given up their time to help us to understand about how we can improve the way that they work. And most importantly, humans are great to collaborate with. And so I'll conclude by saying thank you to all of the amazing humans that I've been able to work with, my colleagues and my friends across visualization, skilled performance, my students who do a lot of the heavy lifting on these ideas. And thank you to all of you wonderful humans out there for your attention this morning. Thank you.
Thank you very much, Chris. That was most amazing, really. The technology that's being applied now to solve these problems is just amazing. I've been involved a little bit with citizen science, and I guess we're the novices at that level who are probably helping the professionals to develop the tools that the computers can use to sort out all the information. Anyway, we might have a few questions there. I think Mark's actually got a question that he'd like to ask.
Well, it's not so much a question, it's more a comment, Chris. I was watching your talk there in the background, and I noticed when you started talking about DWF, I'm like, I know DWF. And then I saw the photo pop up. And my son's actually in that photo right up the back near Eagle.
Oh, well, there you go.
Yes. I don't know if you know Blake Iscaro.
Look, I was not in the room at all during any of the actual.
He did a lot of stuff with Jeff. So that program you put up where they're sifting through the data, he's done a lot of that. I'm like, oh, I know all that stuff.
Fantastic. One of the great things about Deeper, Wider, Faster and that team-based approach is that Jeff's been able to take novices, our work experience students come in, have a great time, high school students, all the way to very experienced senior academics who are very interested in being involved as well.
Well, when Blake started doing it, he was 11.
Fantastic.
Jeff's brilliant, that's for sure. And Igor's work is amazing. What he does with those programs.
Yep. No, it's been great to be on the side, helping to support them to do the science, and lots of different parts of the way that they work have been influenced by some of the PhD students on the screen there, Danny, Bernard, and others. So yeah, it's been, and Sarah, who built this amazing decision support system for them.
Back to you,
I've
Judith.
got a question, Chris. One of the original problems that you had earlier was the temperature control with computers when you're dealing with large amounts of data. How is that changing with the increase in the data that you're having now currently? How are you dealing with that?
So one of the interesting things about computer chips, the central processing unit, is that the faster that you want to do your processing, the warmer the chip gets, and the risk there is that the chip is going to melt. So a lot of the computing technology that's been designed over the last decade or so has been in terms of having multiple chips doing the same thing at the same time. So a lot of that means you don't have to run individual processes as fast. You just have more of them working together. But I think many of us are familiar with the enormous fans that certainly sit in our home computers, and as the processing needs go up, the fan kicks in. And when you're working at very large scale, that's absolutely an issue. When you walk into the supercomputer center at Swinburne, it is so hot in there, and the air conditioners are working overtime in order to get some of that heat out, because you don't want the facility to fail. And it gets even more challenging now when you think about the scale of computing required for something like the square kilometer array. How are you going to provide the energy for that? How are you going to cool it? How are you going to power it? All of those sorts of things. So there's a lot of hard work that goes into designing resilient computer processing.
Yes, we've got a couple of thank yous for your fascinating presentation. Great session from Ergio.
And I'm seeing some
Luke,
thank yous from some colleagues and friends. So thank you so much for
good.
participating this morning. I hope you're going to stay for the rest of the activities today.
I'd just like to add also, as a final thing, that at the Ballarat Observatory, very fortunately, a number of years ago, Chris helped us to get a 3D Astro Tours set up at our observatory, and from time to time, each year generally, we get another movie from Swinburne, and we pay a royalty for having this technology, and it helps to fund a very tiny section of the activities that to go into the virtual reality section at the Swinburne University. So a great legacy that Chris has given us here in Ballarat, and ongoing, of course. Our very recent movie is about exoplanets. So it's an absolute pleasure to have Chris here today, and thank you very much for jumping in and helping us.
It's my pleasure. It's always the Ballarat Observatory is an important part of my life and my career. So I think you do an amazing job there, and all the best for the rest of the presentations today. I'm sure there's going to be lots of very interesting results for everyone to be learning about and discussing.
Thanks, Chris.
Shall we bring John in?
Yes, I think we might move on to our next speaker, and just a little bit of an introduction about Dr. John Wilkinson. He's a member of the ASV and the Bendigo section, and he's going to talk about Solar Section 25. And John is a science educator of over 30 years' experience in teaching science, physics and chemistry in secondary colleges and universities in Australia, and he is the author of over 100 science textbooks. So welcome, John.
Thank you, Judith. I hope that start title is showing up on everybody's, is it?
Yes.
Right, thank you. Welcome everybody. The talk that I'm giving today is on Solar Cycle 25. I've got a particular interest in the sun, and most of the things I'm going to talk about today, they're illustrated with images that I've taken myself of the sun over the duration of Solar Cycle 25. First up, why observe the sun? Well, the sun is our closest star. It has the most influence on Earth of all astronomical objects. And of course, it influences our weather, communications, satellites, astronauts, oceans, plant life. The sun is large enough to observe through small telescopes during the day, but you need caution to do that. You can't just grab a telescope and point it up at the sun. You need special filters or special instruments in order to do that. So I'll remind you of that. And the final thing there, changes in the sun occur all the time. So it makes an interesting object for amateur astronomers to observe. Activity on the sun is monitored by recording or observing things like the number of sunspots, the number of flares, prominences, coronal mass injections. These features vary with a 11-year cycle of changes in the sun's magnetic field, and all these features there are connected with some sort of magnetic effect that's going on. Now, I'm not going to talk too much today about features of the sun, but I will focus mainly on what's been going on in the current solar cycle. So we'll start off with a graph here. This graph shows the monthly sunspot number for cycles 23, 24, and the current one, 25. So if you look here, this is cycle 23, which started down here around about 1996 and went through to about 2009. So this is cycle 23. Cycle 24 started at 2009 and went through this part here down to 2019. And cycle 25, which I'll mainly focus on today, began in December 2019. So we're down here. So the cycles go through a series of minimum here and here and a series of maximum. And the duration from one minimum to the next or one maximum to the next is on average 11 years. So each sunspot cycle lasts that long. Now you'll see here on this graph there, the activity for cycle 23 reached a peak about here, and it was much higher than the peak for cycle 24. And we'll be interested to see what happens in cycle 25, whether it's a high peak or a low one. On this graph, you have the monthly sunspot numbers there in the black line, which varies up and down a fair bit there. And then you have the smooth, or basically the average of those recordings in the red. And the green here is the projected sunspot numbers for cycle 25. Now, the records for sunspot numbers started back in about 1750. So you need to go back then to get to cycle number 1 there. But we're just, as I said, we're going to just focus on the current one here. Now, if you compare that last graph with this one here, it looks very similar, but this one here has got the average sunspot number on the right-hand side here, and the number of flares on this left side. Now, you can monitor the sun's activity by looking at the number of flares or the prominences or the number of sunspots, but they all vary with this 11-year sunspot cycle. On this graph there, you've got the sunspot numbers in the blue here. This is the average or mean for the years across the bottom here. And we've got cycle 23 here, cycle 24 there, and the new cycle 25 here. The yellow bars here represent, the yellow and red bars represent the flares which have occurred. And you can see there that the flares vary with the number of sunspots fairly closely. The flares are graded according to a letter grade here, increasing from A to B to C to M to X flares. You can see here, usually the A and B ones are quite small there, but they're increasing in intensity as we go up. So on here, you can see that the C flares have been plotted. The red bars are the M flares, and the darker bands at the top of some of these represent the X flares. So you can see that we've had a lot more C class flares than the other ones. Okay, now we'll have a close look now at cycle 25 and what's been going on. Well, I said that it started in November, December of 2019. So going on from there, we go into 2020, and the average monthly sunspot numbers for the first few months of 2020 was much less than 8, which is not very high. Because we were at a minimum, we would expect that sort of number. But for a number of months, the sunspot number was at around about 1 or 2. So it was very, very low. We only had a couple of months where it got up to near 8. So I'm going to start the photos that I've taken with this one here, which was taken on the 29th of October 2020. And during this month, the sunspot number count was 14.6. So it started to increase. And from then on, we've seen some gradual rises. Now, the photos that I take are in 2 wavelengths. One is at the H alpha wavelength, which is 656 nanometers, roughly. And the other wavelength that I take images in is at 540 nanometers. So you can tell the H alpha shots there, they're a little bit orangier, and the 540 nanometer shots that I'll show you are more yellowy. So this particular shot, as I said, was taken on the 29th of October 2020, and it shows the active region around here. The active regions are given numbers. This particular one was 2778. So we'll use those numbers for following progress of the activity. So this was at the H alpha wavelength, and the H alpha wavelength are used, it mainly photographs activity in the chromosphere, whereas the other wavelength I used photographs them down in the photosphere. So we've got the photosphere is basically the surface of the sun. The chromosphere is a bit higher up in the atmosphere. And I should mention here, if you look carefully on this particular image there, you can see what looks like magnetic field lines around the sunspots here. And the white area here is due to flaring. Now, this particular shot is at on the same day, but it is at a different wavelength, 540 nanometers. So if I just flick back, you'll notice that it's looking at the same active area, but just in a different wavelength. And this particular wavelength shows the sunspots much clearer. This particular shot was taken on the 6th of November 2020. This was another active area which is on the eastern limb of the sun. And I should mention for these photos that I'm showing you, the eastern limb's on the left, west on the right, north up and south down. This particular active region produced a C7 class flare, and you can see some of the white flaring around the sunspots there. X-rays and ultraviolet radiation from the flare ionised the top of Earth's atmosphere, causing a brief low-frequency radio blackout over the Pacific and Australia. Now, the next day, I took this photo there at the 540 nanometer wavelength there, just to show the difference. If I quickly flick back. So this particular active region's moved a little bit more to the west or to the right. This one produced a C5 flare, and as I said, this is at the 540 nanometers. Moving on to the 23rd of November, this is the sun's southeast limb. We had 3 active regions, one here, one up here, one down here. Sunspot 2785, which is the one just coming into view up here, erupted during the late hours of November the 23rd, producing a C4 solar flare. The explosion hurled a plume of plasma more than 250,000 kilometres across the sun. And then 3 days later, this is the image that I got on the 26th of November, showing that 2 active regions there. So you can see how the different wavelengths show up different, the features slightly differently. next day. This is the same area, but at the H alpha wavelength. If you just flip back, okay, you can still see the same sunspots here and here, but the H alpha wavelength shows more of the magnetic field around those. What's going on? The sunspot number for November is 34.5, so you can see how it's increasing. November 29th, 2020, Earth orbiting satellites detected the biggest solar flare in more than 3 years. And this capture here was by NASA's Solar Dynamics Observatory in the extreme ultraviolet wavelength. And this blast was M4.4 flare. On the 3rd of December, this image shows 4 active areas in the southern hemisphere of the Sun. Active region 2790, 2789, and 2786, and over here 2785. One of the things that became or did occur during this time there was most of the activity tended to be in the Sun's southern hemisphere. There was only one spot in the northern hemisphere. At the start of a new cycle there, this is not an uncommon thing to occur. This image was taken by the Solar Dynamics Observatory 2 there. This was a C7.4 flare from active region 2790 on the 7th of December. Again, this is in the extreme ultraviolet wavelength. December 29th, 2020. This was taken at the 540 nanometer wavelength, showing the sunspots. And the same day in H alpha, this was the image. These particular active regions had stable magnetic fields and produced minor flares. You can also see on this image some prominences here and down here. The prominences look like flames shooting out from the edge of the Sun. But they're basically due to magnetic fields which are breaking through the surface and carrying up some of the plasma from the Sun itself. I should mention that these photos or images that I've been taking are all single exposure images taken through a Canon DSLR camera. Again, here's the prominences on the side of the Sun there. The sunspot number for December was 23.1. It dropped a little bit. This was the 7th of January 2021. The southwest sector of the Sun. There was a nice prominent hedgerow on the southwest limb. You can see that up here. Hedgerow is like a row of tree or hedges along the Sun. At this time, there was no sunspots and no large flares, but this prominence there was a nice feature to photograph, and there's a smaller prominence over here on the right. This particular feature here is called a filament. There's another one just here. Filaments are basically prominences that you're looking down on top of. So if you could imagine this particular row of prominences here, down here, and you're looking down on top. If you're looking down, vertically down here, this is what you would see. Um, 16th of January now. There was, or just prior to this, there was 12 spotless days, no sunspots, but this particular active region appeared with 2 small spots on it. On the 23rd of January 2021, a sunspot appeared in the northern hemisphere, AR 2799. Remember, most of the sunspots prior to this year were down in the southern hemisphere, but we've had this small one just up here. So it was nice to see something in the northern hemisphere. So for the period end of December through to nearly the end of January, this was what the graph for the number of sunspots and flares looks like. So the blue one there shows the change in the sunspot number. You can see here this period of days here where we had no sunspots whatsoever. And the 2 yellow bars there show the 2 days where we had C-class flares. The 17th of February, this is an image that took of the sun, which had some small prominences on it again. This little band around here, like very small little prominence type things, they're called spicules. And moving through towards the end of February, the image on the left was taken on the 25th of February there, and it is in the H alpha wavelength, whereas the one on the right was taken the next day at the 540 nanometer wavelength. So you can see the same active region. So this one up here, 2804, and this one here, 2804 again. It just shows you the what the different wavelengths show. This is the western limb of the sun here on the right side. There was a prominence here, but you can follow it up and over here. So basically this is due to the magnetic field lines that have burst through here, moved up and around and down here, carrying with it the material from the sun. This particular active region up here showed a bit of flaring. You can see that as white there, but it produced some B-class flares. And for February going into March, this was the graph showing the sunspot number changes there. So nothing along here, and then we had some increases here, back to nothing there, and up and down. And these were the days where we had the flares. These orangey ones are the C-class ones. But we didn't have any M or X ones. So you need to remember that because we're at this time, we were at the start of the new sunspot cycle. We do get days where there is very little activity. I put this image in just for something a little bit different there. This was taken on the 16th of March and showed a large prominence on the northeast limb. It didn't only lasted a day or two. The height of this are measured at 116,000 kilometres. So the size of Earth compared with the height of this prominence there, Earth would probably be around about that size. So much bigger than Earth. March 22, there were 2 active regions here, AR 2812 and 2811. And at this stage, I should mention that you get variations in some of the photos that I've taken here just because I might have used different exposures, but mainly due to different atmospheric conditions. Some days the atmosphere is nice and steady and you get really good photos, and other days it's very ripply. These two images were taken by the Stereo spacecraft, which is orbiting the Sun. The one on, or both of them were taken on the 17th of April. They're both different wavelengths, but basically in the extreme ultraviolet. A far-side eruption around a potential active region was observed on this day from behind the southeast limb. The event measured as a long-duration B9 flare and is associated with coronal mass ejection that was directed away from Earth. This is the Sun here. That was the eruption side. This image here on the right is the Sun here is has the diameter of the white circle there. The black area is a mask or diaphragm there, which is blocking out the Sun so that we can see this eruption as it's coming up from the Sun here. So the diameter of that circle there is equal to this from here to there. On the 19th of April, I imaged the Sun, and this was the result there. We've got two active regions here. 2816 produced the first M-class flare for the year. And April the 21st, 22nd, 2817 over on the western limb. Showed some flaring here. And this one produced a number of C-class flares. You can see a few small prominences too. 24th of April, this image, the whole disk one there of the Sun. Again, we've got some filaments here, there, prominence over here, and some nice active regions here, all showing some flaring. Now, on the 26th of April, we had an interesting sunspot cluster, which had 3 active regions in it. So here's the main sunspots here. The white here is showing some flaring, but 1, 2, 3 active regions. And as they approach the western limb, this was the same cluster. If I just zip back there, you can see where it's moved there. But this was taken at the 540 nanometers, so it shows the actual sunspots a little bit differently. Now, the sunspot number for April was 24.5. 12th of May, the first week of May saw few sunspots with many spotless days. Sunspot 2822 on the northeast limb exploded on the 7th of May, producing an M3.9 solar flare, one of the strongest flares of the new cycle. And this particular shot shows the northern hemisphere of the Sun in a nice active region 2824, showing some flaring and magnetic field effects around it. This produced a number of C-class flares and coronal mass injections over a few days. The sunspot number for May was 21.2. This is the 22nd of June, and active region 2833 over here, and a nice filament here, some prominences around here, the filament there. Low levels of activity occurred during June, and the Sun remained fairly stable. Except right at the end of June, we had this down in the southern hemisphere, active region here, and another one here. And the image on the left, again, is the H alpha one here, and the 540 nanometer one here, just so that you can see the difference. The sunspot number for June was 25.4. This was the 3rd of July. There was an X1.5 flare on the northwest limb. This was the strongest so far of cycle 25. It is over here. And the 15th of August, there was a really good prominence on the northeast limb. That looked quite spectacular at that one. And the 24th of August, there was a coronal mass ejection prominence eruption off the west limb and 2 C-class flares near AR2859, which is shown over here. This particular image, again, is in the extreme ultraviolet there. This was taken by the Solar Dynamics Observatory. 28th of August at 540 nanometers, we had 2 active regions, 2860 and 2862. I remember these sunspots, the sun rotates from the east over to the west. And this particular image there is the same date, but at H alpha wavelength, just to compare it. There's a flare here of 4.7. I'll just flick back there so you can see. And if you keep your eye on this part here, this active region here, you can see there it is there. Now you'll notice that in order to see the prominences, these features along here, you can only see them at the H alpha wavelength. You can't see them at the 540 nanometer wavelength. If I flick back, you can't see them there. So the different wavelengths show different features. 6th of September at 540 nanometers, we had 1, 2, 3, 4 active regions. So it was, as we're getting into the new cycle there, we're getting more active regions and the sunspots are starting to get a little bit bigger. But this particular day there, they showed up quite nicely. And on the 9th of September, at 540 nanometers, we had quite a bit of activity as far as the sunspots went. So we've got 1, 2, 3, 4, 5 active regions there. You know, one of the things on these is that I've listed down there at the bottom. Are these big? Well, let's have a look. If we go back now to the previous cycle at the maximum, here is an image that I took on the 23rd of October 2014. So this was at the peak of cycle 24, the previous one. And this was the sunspots. This particular active region measured 140,000 kilometres across from here up to here. And the mean sunspot number for this particular month was over 100. So if we go back to there, yes, we've got sunspots for this cycle, but you can see that they are fairly small. The same thing with the prominences at the moment. They're fairly small. They're not as large as when you reach the maximum. Okay, now back into our current month. So this particular graph goes from the 30th of August through to nearly the end of September. But the blue graph there shows the variation in the sunspot number, and the orange bars there show the number and intensity of the flares. So most of the flares are C-class ones. and we did have M class 1 here on this date, which is the 23rd of September. And if I move here, the 23rd of September, so that flare, that red part there, the M class flare, came from here, where the white areas are. So that was active region 2871. So you can see that we're starting to increase in the number of active regions around there, and the sunspots are still relatively small, but as we go into the new cycle, they'll start to get a little bit bigger. Okay, we're nearly to the end now. So if you have a look at this particular graph there, this is the observed monthly sunspot number in the thin yellow, this line along here, and the observed smooth monthly sunspot number in turquoise, which is this one here. So this is basically the mean of this, or the average of this yellow one there, and the magenta crosses, which run up here, are the predicted smooth monthly sunspot number. So astronomers are expecting cycle 25 to follow the purpley crosses here. So we're looking for a maximum around about middle of 2023, maybe going to 2024. Astronomers or solar astronomers vary in their opinion of when the maximum will occur and how high it will be, depending on which particular model they follow. So just to finish up, the instruments that I've used to take the images that you've been looking at, the H alpha ones were taken through a Lunt 100mm scope. This particular scope is just used for solar observing. It has energy rejection filter up here, and it's got special filters in here called echelons there. There's a tuning, pressure tuning device here, and this is where I mount the camera to take the images. This is the focuser here. This is a diagonal here. I won't go too much into that scope there, but it is solely used for observing the sun. If you have a look at the night sky through that there, it's just totally black. You don't get anything. So it's geared up for looking at the sun in the H alpha wavelength. And the other instrument that I use is this one here. This is used to take the images at the 540 nanometer wavelength. This is a William Optics refractor, 81mm one, with a Barder Herschel wedge down here. The heat and light from the sun goes down here. There's a special screen which lets out most of that heat and light, 95% of it, and only 5% of the light goes up here into the eyepiece there where you have a look at. So it's a fairly safe area. Again, this Herschel wedge there is a special device for looking at the suns. In here, there's a 540 nanometer filter there, which gives me that narrowband images at that particular wavelength. Okay, so that's a fairly brief overview of things that have been going on for cycle 25. So I hope you enjoyed that. Okay.
Thank you very much, John. Sorry. Yes, thank you very much. That is absolutely fascinating, an excellent journey over the progression of solar cycle 25. So we did have a question, but you've answered that with your last slide of the equipment that you use. So
all right. Okay.
we'll just see if we can find another.
There is another
Question?
question from YouTube. Ken wants to know
All
who
right.
assigns the AR numbers, what defines an active region, and is there a maximum separation or number of spots?
There may be a separation for the number of spots. Basically, when a new sunspot group forms, and it may form anywhere on the surface there, it's given an AR number, and there's a body in America there that assigns those numbers. Usually when a new sunspot group forms, it will appear on the eastern limb and then travel across to the western limb. When it goes off the western limb, it will go around the back of the sun. It may last the full journey around the back and then reappear on the eastern limb. If it does reappear, it's given a new AR number. Sometimes you get new groups forming while it's over on the western limb, and it's still given a new AR number.
Thank you, John. There is another question, and Lenny's wondering how spectroscopy can add understanding of sunspot activity.
Yeah, that's an interesting question, and I might leave that one there to somebody who's fluent in spectroscopy, but it can add to that. But yeah, that would take a very long time to explain there. So I won't go into that area because it wasn't one that I was looking at today. But yeah, so it can add to it, but I won't run into that now. Otherwise, we'll run over heaps of time. So
There's one that's just popped up, Judith. Another one.
That's a good lead-in question to our next session. All right, I'll just comment about this. That's actually a good lead into our next session, which is the Zoom room, chat room, and coffee room. Somebody might there like to expand on Lenny's question about spectroscopy, using it on the sun.
Yeah. So the colour of our sun is it's being a star, but it's a yellow star.
Did you have another question there? Sorry.
Yes. Some of the images that are taken of the sun, however, appear in different colours, just to represent the different wavelengths that we're looking at. But basically, the sun is a yellow star.
I don't think there are any other questions that I can see, Judith. So most of them have been answered wonderfully by Russell in the chat.
Yeah. Yes. Well, I'll open up the Zoom room if anybody wants to grab a cup of coffee and have a little relaxing chat, catch up with people.
No worries. And I'll end the stream here for us now, Judith. So thank you, everybody, for coming along. The next one is at 11 o'clock. Is that right, Judith? I believe it is, yes. 11 o'clock with Phil Hart and you as well giving a presentation.
Yes, good.
So we'll be back in
Thanks very much, Mark.
That's all right. We'll be back in 24 minutes.